Morning everyone, this is lecture number 38 for digital MOS LSI circuits E524, and today is November 21, 2020. So this is the last topic of our course, and this is the last lecture for our course also. However, this course does not stop over here. If you want to go for some higher things, you can go for some course called Digital VLSI Architecture, which is coming in the next semester, and it's going to be taken by Dr. Rahul Shrestha. So for this particular chapter, I'm following again the book Rabe, and I'm following the chapter number 10. Some of the important topics which needs to be known, or you can say that it's very important in terms of getting job in digital domain, because most of the time when they are taking some written test, they are asking the questions which are actually taken today. So some of the questions I took it today so that you can understand what kind of things you need to know. First of all, look, digital system is classified on the basis of what kind of interconnects you are connecting. You must be knowing about synchronous and asynchronous. Synchronous is the one where the clock is same and there is no change in terms of clock at all. However, it's difficult to achieve that thing. So in that case, there are two new systems like mesochronous and plesiochronous. Both the words are Greek words, and the meaning of meso is actually middle and plesio is near. So here all the frequencies, like all the blocks, are getting same frequency. Here frequency is same in mesochronous. However, phase might be a bit different. And here nearby frequency, but not exactly same. And asynchronous is already known to you, right? So all will have a different frequencies you are applying. Now let's start from where we have stopped. So by the way, this particular chapter is actually the extension of what you have studied throughout the course. However, if you remember, in the case of sequential circuits, where we were talking about time t, which is acting as a clock period, has to be greater than contamination delay. So this is coming from the logic delay. Either this is going from clock to Q, and this is setup time. Okay, and if you are talking about how much hold time has to be known to you, that is depending on two things. It has to be lesser than the contamination delay and the logic delay. It's not dealing with setup time at all, right? But it has to be lesser than these two in total. If you look at this particular diagram, you can see that delta is actually a delay. T clock is same as the clock period you are giving, right? So this is the clock period plus extra delta time, which is here. So in general you are saying delta, but you are more interested in delta plus hold time, right? So in this case, delta is actually greater than 0, right? You can see here delta is positive, clock 1 and clock 2. So clock 1 is the reference one, then it's positive 1. But if it is reverse one, where clock 1 is little bit delay, then delta becomes less than 0. Means in this system, delta is less than 0. So if you want to accommodate delta also in this equation, these two are the main two equations. So in that case, t plus delta, which is t is nothing but actually it's the expected t clock, right, has to be greater than or equal to rest of the quantities like contamination delay, logic delay, and the setup time. And if you are taking this delta other side, This is the new equation. Similarly, for the t hold, you can write down delta plus t hold has to be less than the equation, which is like taken over here. So there are two equations, 1 and 2, which are modified by adding delta extra over here. So delta will go that side, and you can find out the exact value, right? Now let's understand there are two kinds of clock skews. It might be positive, it might be negative. So here you can see that this particular system, the first one, is a positive clock skew because you are starting the clock from here. But because of interconnect and other delays, like clock 2 and clock 3 are getting the positive delay, right? Or you can say that it's a positive clock skew. Whereas if clock is starting from other side, T clock 1 is actually delayed version of T clock 3, the reverse of what happening for the first block first diagram. So in that case, the first one is the positive skew and the negative, second is the negative skew. The other thing is whenever you have the feedback, positive, negative, whatever kind of feedback, you will always experience the negative skew because it's running at that particular speed. And if you're looking at the open loop system, so from this clock to this clock, all these are getting the positive clock skew, and that is going to give you the different answer, right? Or it has to, these resistors has to wait for at least that much time, right? So that they can generate the output. So those things has to be accommodated in your analysis so that you can have the exact number of exact number or exact value of clock. So the most important part of such system is you need to find out what is the value of clock you can apply over this. For that, you should know following things. You should know what is the delay coming from the logics or the contamination delay from the resistors because they are the sequential circuits. And of course, you should know the setup time. Along with that, for the knowing the what should be the hold value, that has to be derived also from the sequential circuits, which says that you have to make sure that the contamination delay and the the logic delay should be higher than what t hold value you have. And for the t clock, as we already know, it has to be greater than or equal to contamination delay plus the logic delay plus the setup time, right? And considering the delta delay, which is coming from this skew, either in positive side or negative side, you can design the resistors or logic separately, or you can apply clock after knowing what will be the value, right? Now let's take one example. So we are, it's better to go with the example rather than going into theory much. So this is also example taken from Rabi, which says that consider the logic network shown in figure. Okay. Now determine the propagation and the contamination delay of the network, assuming that the worst case delay from each gate is T gate. The maximum and minimum delays of the gates are same and they assume to be identical. So means all the delay of the gates are T gate. Now, if I want to find out the the delay, let's start with the like propagation delay. You can see that there are two paths has been shown over here. So one path is this one, and another path is this one. But before jumping into the answer that what will be the propagation delay, because here in two parts, you might say that the propagation delay is equal to 5t gate. It might be wrong also. So let's see how it's going to be derived. So let's assume that here, I'm removing these two parts one more time just to understand how these are derived. Let's assume that the, or maybe I can make this circuit again so that it will be easier for you to understand. So following things are given, right? So now look, the output is governed by OR gate, right? So OR2 is governed by two things. One is this one and one is this one. Now, any one of the output is 1, then you are land up in 1, no problem. Means if this is 1, you don't care what is coming here. At the same time, if this is 0, you don't care what is coming here. Again, the output is again, this one is 0. If this is 0, this will also become 0 and this will be 0. So OR2 is actually depending on only and only the output of this one, not on this one, because this will be decided if this is 1, right? So even if this is 0 and if this is 0, the output of this one is 1. Whereas if this is 0, it doesn't matter what the input is coming from here. This is 0 and this output is 0, right? So actually, this part is important for us, first of all. Now let's see that in these three gates, are they really important or not to us? Because the output of this one, either 1 of 0, it's depending on following things. Look, the output of this one is 1 when either of these two are 1, right? So it's depending on these two for sure. You cannot avoid any one of them. There might be like all four conditions will be there: 0, 0, 0, 1, 1, 0, and 1, 1. All four conditions, this is important. So this is also important. You can't avoid it. But for this one as an input, does it important for you or not? Actually, it's not, because this input of N3 is actually taking input and only from the or output of the OR1. It's depending on that. If this is 1, like I know that OR2 output is also 1 without knowing other inputs. And if this is 0, without knowing what is coming from here, this is 0 and output is also 0, right? So in reality, the important path which is going to decide the output is actually on this path. However, another path was also drawn, which was here, which was taking 5 gates in a path, but the critical path is actually the one where the logic is changing and output is depending. So on the logic, on the critical path, there are 4 gates are coming, and that's why the propagation delay is 40 gate, as the delay from each of the gate is only 4. Similarly, like if you want to find out the contamination delay, I'm keeping up to you people. You can find out it's 2 T gate, which are coming from 2 OR gates. And whenever the signal is available, it's only depending on these 2 OR gates. You can think about it, why it's there. It's given in the Rabe book. Now, okay, it's already in the, this is the solution. Okay, so which already we have discussed. Now, there is a silver bullet. This is very important thing, and it's a very useful information which is written here. The computation of the worst case propagation delay for combinational logic due to the existence of false path. So here you can see that the path 1 was a false path. Means even it's there or not, it doesn't matter, right? So on path 1, there were 5 logic gates, but still we are not considering that, because we know that it's not going to be the it's not coming on the critical path. The critical path is the one which is not the false one, and it says that cannot be obtained by simply adding the propagation delay of individual logic gates. You have to find out the critical path on which there are logic gates are coming, and accordingly you can find out the answer. So the The critical path propagation delay does not mean that more number of gates. Okay? That's why this example has been taken, right? So it's not the direct answer. Okay. Now, as we know that we have studied about jitter, it's happening at high frequency, and you might see that going from 0 to 1 and 1 to 0 might not give you same answer, right? Every time that that will have some fixed time interval error. So same thing has been drawn over here. And if that is the case, then understand that jitter will have plus and minus values. So plus and minus 2t jitter will be there in total. So now if you want to find out the clock value, it has to be t clock minus 2t jitter has to be greater than whatever we have derived. The contamination delay, logic delay, and setup time. If you take this 2t jitter that side, then the clock has to be bigger than contamination delay, logic, setup time, and twice of jitter, all in total. It has to be more than that. Okay, if you are when you are making the budget. Okay, now I have taken these two examples from the solved examples of Rabe. So this is from there. So you can follow that. So here you can see that there is one circuit which is already given in uh, chapter number 7. I don't know whether you remember it or not, but this is the figure from there. And there are following things. One is the input D, one is clock, one is clock bar, but clock bar is actually derived from 3 inverters. Okay. And here something is written. Let's start from there. Assume that all the transistors have been sized such that the delay from any input to the immediate output equals T invert is equal to 100 picosecond. Let's write down somewhere that each one of the stage or each one of the gate will have 100 picosecond of delay. So if you are talking about delay from here to here, that will be 100 picosecond. If you are talking about delay from here to here, it's also one stage or the one logic gate. So 100 picosecond. If you are looking from Q to the output of this one, that is also 100 picosecond. And even this one also, like there are 3 inverters, so from clock to clock D bar is going to have 300 picoseconds of delay, right? So if I want to draw clock, which looks like this one, clock, if I am going to draw clock D bar, it's going to look like this one. So this delay is 300 picosecond, right? And the name of this one is clock T bar. Okay, so now note that the external clock is operated at 1 giga, means this value of this one is going to be 1 nanosecond, and this will be 500 picosecond, right? So out of which 300 picosecond took time to get settled for giving output clock T bar, right? So draw the waveform at nodes clock D bar, X and Q for 2 clock cycles with D equal to 0 in one cycle and D equal to 1 in other. So 1 and 2. If this is D, right? Now, what is going to happen? Let's start from there. If clock is 0, the output is 1. When clock is 0, right? So when clock is 0, output X, because we need to draw X and Q both together. So X is actually 1. So this is 1. But note that whatever the value it was after 100 picosecond, this is happening, by the way, because if you understand that, look, for any input to the immediate output equals 100 picoseconds. So from here to here, it takes 100 picoseconds to change the state, right? But when it's equal to 1, when clock becomes 1, this is off. And now it's depending on following things. Those following things are, this has to be 1. This is one condition. D also has to be 1. If it is not there, then X will remain at the same place where it was, right? So D is actually 0, so it makes detachment from here. X remains at where it was. So you have to have D equal to 1, then something will happen. When D equal to 1, it also wait when clock D bar becomes 1. And also, like, there is a small time when it's propagating, right? So in small time, X will go to 0 and then come back. And similarly, for the Q, between X and Q, there is a propagation delay of 1 stage, so 100 picosecond. So this is 100 picosecond. And you see that this is going to be 1 to 0. By the way, this particular scheme is known as the pulse register. If you want to see the output, which is drawn over here, it's shown. Okay, I made a mistake over here. It has to be latched because of the this NOT gate. It's going to be latched, right? So this scheme is already known to us. This is called pulse register or pulse triggered latch, which we have studied. It's again what we have studied on, right? So all these dotted lines are 100 picoseconds each, and that's how this has been drawn. Okay. Now let's go to the second question for the same circuit. That are the setup time and hold time of this sequential circuit positive, negative, or approximately 0, and why? Look, the setup time of this circuit is negative because delay from input to the output is smaller than the pulse width. If you look at this, input to output is smaller than the pulse width, so it's actually negative, right? If it is coming like this, then it's becoming positive. If you look at the circuit, the diagram which we have started with, look at this, then it's a positive, otherwise it's negative, right? So same thing is happening over here, that in this case D to Q is actually delayed one, that's why it's a negative setup time, and the whole time is positive because the D input must hail setup value settle at node X and node Q, right? So this is another aspect. Now you need to calculate the different values, like you need to calculate the propagation delay T clock Q for output high to low and low to high. So we already know that the propagation delay from one inverter is actually 100 picosecond, right? So going from low to high, it's only one stage which is creating whole hurdle, which is T inverter, right? So it's 100 picosecond. For low to high, it's two inverters, so it's 200 picosecond because there are two stages, right? So this is also quite easy. But now the question is, can you reduce the number of stages which are kept here, 3, between clock and clock D bar, from 3 to 1? And why or why not? Look, if you reduce it to one inverter, what is going to happen? I recommend, like, you can simulate also in Simica, or you can also analyze. The answer is already given over here, but that can be only understood when you're going to do the experiment, right? So you can analyze it also if with single inverter, what is going to happen. Note that single inverter should have 100 picosecond, and with the all same facts. You cannot make that like one inverter having 300 pico and rest of them having 100 pico, right? So if all have 100 pico, what is going to happen? So this is sometimes this is an interview question also, right? Okay, now this is the last example where, like in this problem, there are two resistors and two logics are given with the values of T max and T mean. By the way, this value is actually 10 nanosecond, not 8. So he is saying that T clock Q2 max is equal to 4 nanosecond. Clock Q mean is 2 nanosecond. Setup time of this resistor is 1 nanosecond and hold time is also 1 nanosecond. Right? So these informations are given to you and you have to find out other things like what is the maximum operating frequency of the system if there is no skew and jitter. The skew and jitters are not there. If you remember, the equation for finding out T is contamination delay, then logic delay, and the setup time, right? All these are the max one, by the way. We don't care about the minimum one, right? Minimum is important in the case of hold time. By the way, for the hold time, if you want to find out, then it's TCQ minimum plus T logic minimum. So even smaller than that one, the T hold should be. So these two are the standard equation. So in that case, TCQ max, T logic max, and T setup. Setup is already known to me. It's 1 nanosecond. T logic max is already given to me. It's 25 nanosecond. And TCQ max, which was given as a part of this example, that it's 4 nanosecond. So 4 nanosecond is coming from there. If you make the total, it's giving 30 nanosecond for the first one. So the requirement of the clock with the logic 1 and resistor 1, it's derived as 30 nanosecond. In other case, applying same things, you can have TCQ max 4 nanosecond. This number is 20 nanosecond and T setup time as 1 nanosecond. So it gives you 25 nanosecond. So among these two, the bigger one is 30 nanosecond. So 1 by 30 is going to give you 1 by 30 nano is going to give you the required clock frequency. So you should not give 1 by 25. You have to take the bigger one so that you can have the correct answer, right? So if there are multiple such stages are given to you, then you have to make sure that you check for all and the maximum will be taken into account. This is also one of the famous example or famous question which is asked in all the competitive exam or maybe in case for company jobs. Now the second one is what is the maximum random clock skew that is system can tolerate. So if you look at the previous equation where skew and hold time are very important. So T skew, which is actually the delta, plus T hold has to be less than TCQ mean and T logic mean. So minimum time. So now you have to consider this 5 nanosecond, and as I told you, this has to be 10 nanosecond. So 10 nanosecond that has to be taken into account. If you keep these two numbers, you will see that TCQ minimum is 2 nanosecond. For TCQ mean, it's 5 nanosecond, and hold time is 1 nanosecond. That's going to give you 6 nanosecond. And again, for the case of second stage, you can find out the number that is coming around at 11 nanosecond. But because you are interested in the minimum of any from any of these two, so it's coming out as 6 nanosecond, right? Because in clock skew it has to be less than what value is given to you, right? Now this must be the last question. So assume there is no random skew and you are able to introduce the clock skew into this system. How do you route the clock and add the skew to maximize the system? performance without sacrificing the functionality. Okay, so the positive clock skew will be coming there because of the feed forward path. You can't avoid it, as there is a positive, like there is a like feedback path is there. So in that case, you will have the skew, but because of feed forward path, you will have the negative skew in the system, as we have already seen with the theory. As a result, we can introduce positive skew of 2.5 nanoseconds. So this is a budgeted number. So I already know that there is some number 2 nanosecond has to be given. Yeah. So this one is 2 nanosecond is already given to me. So in that case, I'm instead of taking 2 nanosecond, I'm making one budget that number will be little bit higher than that one for having the positive skew. So that will be zero point 0.5 nanosecond. So this will create a positive skew along with the fit for part to maximize the overall performance. So if we need, so with this number, which was earlier 25 nanosecond, so 1 by 25 nanosecond plus 2.5 nanosecond will give me 27.5 nanosecond, and that's going to give me 36.4 megahertz of clock. And as we know that this equation is the standard equation for a case where clock skew plus 2 times jitter plus t hold has to be lesser than these two numbers. If you do that for both the stages, you will have some answer. So in this case, you are going to take the minimum of these two, which is 3.5 nanosecond, and because of t jitter max is actually half of what you have achieved, so it's 3.5 divided by 2, and that makes 1.75 nanosecond.